Uh, I'll just wait for some time. Sorry, I mean, I had some technical issues. That's why I was off for a couple of minutes. I guess I'll start and probably then the students will join in. All right. So welcome all to the week 5 live session on NPTEL NOC24 EE-143 tutorial. This course is Semiconductor Devices and Circuits with course instructor Professor Sanjeev Sambandan from IC Bangalore. I'll be the teaching assistant for this session, and yeah, we can go through the guidelines. In case anyone has doubt, he can raise any query or just type it in the chat window. Please ensure that the microphones are muted when you don't intend to speak, although there is no one in the meeting right now. I wish someone would have joined this meeting because this won't be an interactive session otherwise, right? This would just end up being a recorded session. I guess I'll wait for 5 minutes. I'll wait for 5 minutes and I hope someone will join. I'll proceed. It's too late right now. So yeah, the recording link for this session would be duly shared by the NPTEL course team, and you'll also be provided with the lecture notes. So the prerequisites include the last week's lectures, which covered the topics like metal semiconductor junctions, the Schottky contact, their electrostatics, and the IV characteristics of them. So yeah, these were the 3 topics, I mean, that I intended to have a discussion upon. But since there is no student in the meeting, I'll assume no one has any doubt. Okay. Feel free to get in touch with me. You can either mail me or, I mean, ask me in the next meeting. So let's start with the first question. So the first one is that a student he decides to fabricate a metal semiconductor junction using zinc oxide as a semiconductor and gold as a metal. Okay, so the question is what sort of a contact at the junction can the student expect? Should he expect that it would be an n-type ohmic contact? Should it be an n-type Schottky, p-type Schottky, or a p-type ohmic contact? Please attempt this and let me know in the chat which option do you think is the right one. I'll repeat this question once. Am I audible? Can you at least type in the chat yes that I am audible, because no one yet confirmed. If I'm audible to you, just write in the chat yes, and I'll get to know that yeah, I'm audible. Okay, I'll hope I am audible. So how will we proceed for this question? I mean, we need to compare the work functions of the two materials, right? The zinc oxide, the semiconductor, and uh, this metal, gold in this case, right? And accordingly, we'll take a decision. Please attempt this and let me know. Yes, anyone, please. Would it be a short key? Would it be an ohmic? Would it be a p-type or would it be an n-type? You guys attempt this. I'll just take 2 minutes. Okay, so no one yet responded. So if you'll, use the values of the work functions of these materials, it turns out that the band diagram that will be formed after, making, sort of a contact at the junction would be something following, right? You'll have something, why isn't, okay, sorry, my Apple Pencil battery is down. Will just take a couple of minutes. So meanwhile, try to form the band diagram. How should the band diagram look in this case? You have ZNO, right? What is the work function of zinc oxide material? Work function of zinc oxide is around 5.13 electron volt, right? And what is the work function of gold? Work function of gold is 5.1 electron volt. Okay, so yeah, it's 5.1. Let's take it as 5.1. So now how will this, band diagram look? Hope this would be charged. Yeah, it's 10% now. Should work. Hopefully. So this is how the band diagram would look. Right, this is your EV, this is your EC, and this is your EF, right? This is our ZNO, and this is our gold, right? Fine. So this is, I'll write this as, this would be N-type short key. I mean, the justification for this is that your, work functions are such, right? As I said, work function uh, gold, for gold, it's taken about, it varies. The variation, the range can be anywhere between 5.1 to 5.47 electron volt, right? While for this zinc oxide, uh, the data that I have access to, the zinc oxide, it can be around 5.13 electron volt. Okay, so if you make the equilibrium band diagram, it would look something like this, which is nothing but an N-type Schottky contact. Now the second one, uh, consider a metal semiconductor Schottky junction. So in this question, the question itself is saying that it is a Schottky junction. So the doping profile in the semiconductor ND, it varies as a function of length as follows, right? Your, what should I say? This ND of X is equal to N0 e power alpha X sine of Px, right? This is your doping profile in the semiconductor. Now, assuming the full depletion approximation, the ratio at of this electric field at x equal to xd by 4, x equal to xd by 2, that is your this particular ratio, right? Your electric field at x equal to xd by 4, electric field at x equal to xd by 2. This particular ratio is of the form your k sine of theta 1 by sine of theta 2. Okay, this is your, the ratio of the electric field looks something like this. So now this from Gauss law we have following, right? From Gauss's law you can write that your del dot E is minus rho by epsilon, right? And you know this, right? So you probably know this term, right? So if you use this in this equation, uh, and also you can do one simplification. See, uh, managing this exponential can get tedious. So what we can do is we can use the following approximation, right? Your e power x, right? What is the Taylor series for e power x? Can anyone at least type in the chat? What is the Taylor series of e power x? Something that should be, understood, right? What is it equal to? Just type in the chat or just unmute yourself and let me know. I'm asking what is the Taylor series of e power x, right? What is this? Can anyone just type it? Okay, first two terms. All right. So the Taylor series of e power x is 1 plus x square by 2 factorial and so on, right? So, if we take only two terms, right? It's 1 plus x. I mean, this is what it is. 2 factorial plus x cube by 3 factorial and so on. But what I'll do is I'll only take first two terms, right? This is actually a good approximation, especially when x is small, right? So I'll use this approximation for my ND. What will my ND become? My ND of x would be approximately N0, my 1 plus alpha x and my sine of px, right? This is what ND would be. Fine. Now this is your ND, and now you can go ahead and plug that into this equation, and from this you can then compute the value of k, right? It turns out that the value of k is 1.5. Okay, just check it. You can either check this while the session is ongoing, or you can just let me know later. Okay, I want you to do this exercise. Okay, just try this, how k comes about as 1.5. Now third question. Okay, it is said that an ideal Schottky contact is formed between the metal that is having a work function of 2.8 electron volt, and an n-doped semiconductor that is having a dopant concentration. Okay, the dopant concentration is 10 to the power 5. Okay, so the dopant concentration is 10 to the power 5 per centimeter cube. The band gap, yeah, is 1.1 electron volt, and the affinity, electron affinity chi, that is 2 electron volts, right? We need to, approximate what is the barrier height at the metal semiconductor interface, okay, in electron volts, obviously. So we'll do the following. Okay, we need to make band diagram. So we'll write as follows. So this is Schottky contact between your metal and your n-doped semiconductor, right? And your phi m is greater than phi s. Let me make the band diagram now. Let this be the interface and this be the Fermi level. This would be EFS and this would be your EFM. Equilibrium, the Fermi level is constant throughout. Now your EVAC, right? Let me use green for this EVAC. This is your EVAC. Right, since, I mean, I hope this is understood, but still I'll write it. This is your metal and this is a semiconductor. Right, and this is the interface. Okay, now we know that the work function of the metal is 2.8 electron volt. But what is work function by definition, right? By definition, it is EVAC minus EFM, right? How much, I mean, how much is the energy difference, right, between the vacuum level and the Fermi level in the metal side? So if this is EVAC, if you compute this, it's given that this is 2.8 electron volt, right? And electron affinity is 2 electron volt. Okay, 2 should be roughly somewhere here. So I guess I would draw something like this. Yeah, let this be 2. Now what about EC, right? So okay, just a second. The band gap is 1 electron volt. This is an n-doped semiconductor. Okay, done. Right, this would be your, this is your EC. Okay, and this is your EVAC. How much is this distance? EVAC minus EC is electron affinity, right? And it is given that the electron affinity for this semiconductor is 2 electron volt, right? And then, I mean, then we also know that the band gap is 1 electron volt. So I guess it should be roughly something like this. I mean, maybe it's not drawn to the scale, but yeah, still. Good evening. Where would be the previous year papers for practices? Mm, I don't have any idea. I mean, you need to contact the NPTEL team for that. Just drop them an email and probably they would get back to you. Just write them that. I mean, also, I'm not even sure if, I mean, they will provide you previous year papers, but still, I mean, it's worth a shot. Just mail them and tell them that you need the previous year papers. I mean, is that possible? Can anyone confirm? Has anyone done that before for, I mean, yes, I mean, other courses? Okay, you have done the mail, but there is no reply. But when did you drop them the mail? One day before yesterday. I mean, I guess you should wait for a week at least, right? It's early. But in the case they don't reply, I mean, just assume that they cannot provide you that. But if they do reply, then you will have the answer, right? Is that it? You had emailed to course teacher too. Yeah, fine. Just wait. They will probably get back to you. I mean, you mailed the right persons, right? They are the ones that know this part, right? Fine. Let's proceed. Okay, fine. So I guess this is your 1 electron volt. Pardon, I guess this is not drawn to scale, but still, assume this is. Okay, so the barrier height at this interface is approximate. What is the barrier height? Can anyone, I mean, point out what is the barrier height? Saying that the barrier height at the metal semiconductor interface, that is what we are interested in, right? We have the following information. I mean, we know the work function of the metal. We know the, I mean, electron affinity on the semiconductor side. We know the band gap. What else do we know? Okay, we also know that we have n-doped semiconductor that has a dopant concentration of 1 into 10 to the power 5 per centimeter cube, right? How will we compute phi b? And the more important question is, what are the quantities that we shall be needing, right, to compute that? So this would be the barrier and this is your phi b. Now, can anyone just compute what this phi b is numerically and then type in the chat? Please do that. Yeah, Jaskaran, can you just confirm if I'm audible? Although I do think I am audible, but still. Okay, fine, I am audible. Thanks. Please do this exercise, right? You need to compute what is this, right? This part. What do you know? You know this part, right? And what is phi b? Phi b should be this whole minus this. But the question is, do we know this? Do we? Is this clear? I mean, this part is known. Do we know this part, this orange part? Okay, let me rephrase this. My claim is we know that. Can anyone tell me how and what is this orange portion equal to? Hint is you can just, I mean, look at the given quantities, right? One of the given quantities corresponds to this. And that is what I want you to point out. Prasadra, I mean, noticed you were trying to say something, but you were not audible. You can probably type in the chat if you are facing any difficulties because I was not able to hear anything. Please type in the chat unless you have a working mic. Let me give you a hint. What is this? Electron affinity, right? This is electron affinity. Same electron affinity, and electron affinity. Isn't it? Why? Because EVAC and EC, they are equidistant throughout the semiconductor. So their difference would also be constant throughout the semiconductor, right? So if it is 2 electron volt here, it would be 2 electron volt here. Okay, now that you know this, can you compute this? This is straightforward and I seriously expect an answer this time. Otherwise, I mean, if you're not able to understand, just tell me what is the issue and why you're not able to answer this part. Is it that hard? I mean, I'm telling you that I want to know this. I know this. I know this. What should I do to this? 0.8. Yes, this is 0.8. Thank you. So this would be 5B and our 5B NPTEL would be 2.8 minus 2 electron volt. That is equal to 0.8 electron volt. So this is what we were, I mean, required to compute. Right? It was pretty straightforward, right? All you, I mean, needed to know was that electron affinity chi remains constant throughout the material, right? So we only use that fact and rest this question was simple. So yeah, I guess I should write it here as well. So this is 0.8 electron volt. What about this question? This looks like a big passage, right? But still, give it a read. Once you are done with reading it, just type in the chat that done or just write that we read it. I'll wait. Read it carefully. I'm waiting for a text in the chat, okay? Once you complete and finish reading this, just type in the chat that we are done reading it, and then I'll proceed. Email address of the NPTEL team. I mean, I thought we were asking a query related to this question. I mean, that should be on the website, right? You may do one thing, you may ask course instructor for that, okay? You may ask him which email address should you contact, right? And please wait till he replies. Wait patiently. It's only been a couple of days, right? So you can probably wait. Okay, coming back to this question. Did anyone read it? Prasad Rao, you are unmuted, right? Is it intentionally or you have just accidentally unmuted yourself? I'll mute you. Okay. In case you have any query or you want to say something, you can just type in the chat. Okay. I'm assuming you have accidentally switched on your mic. Okay, let's get back to this question now. So we are given following. I mean, let me use a different page. Okay, let me first read this out still because nobody said that we read it. So I'll do that myself. So as part of a mini project, a student wants to design a circuit that can set the time constant of a multi-vibrator on a chip. Since it has to be laid out on the chip, most of you might have already guessed that we cannot use discrete components, right? Like, for example, we cannot use discrete components like R and C, resistor and capacitor. So this means that we shall need to make use of certain properties of semiconductor, right? That were taught in this week to build this circuit. So let's help this student out. Of the two components that were needed for the purpose, let's have a look at the first component. Okay, so now I mean, this question will describe are what is this first component, right? Bear in mind that we'll be using a semiconductor, right, for it. So it is a bar of an N-type semiconductor. Fine, it is N-type. So it's having a length of 1 centimeter and area of cross section being 2 centimeters square. The concentration of donor impurities is 10 to the power 15 per centimeter cube, and the mobility of electrons is 500 centimeters square per volt second. Okay, so this looks like a resistor, isn't it? I mean, we are having a bar of length of some particular length, having a particular cross section area. Mobility and the concentration of the donor impurities, they would correspond to some sort of conductivity, which in turn would correspond to some sort of a resistivity, right? So from R is equal to rho L by A expression, we can compute resistance, right? So we shall do that first. I hope I was clear. So this is what I mean. We are having two components, right? This is your component one. In the component one, clearly, as I mentioned, it is a resistor, right? And we'll use uh, R is rho L by A for it, right? So rho is 1 over sigma and sigma is NQ mu, right? So this would be your L N Q mu N A. This would be, what is L? L is 1 centimeter, right? Whole divided by N. What is N? Here N is, we can take that as the concentration of donor impurities, right? So I'll write N as 10 to the power 15, right? And your mobility, that is 500. And what else? Unit charge, that is 1.6 into 10 to the power minus 19 times the area, and area of cross section is 2. Fine. So area of cross section is 2 centimeters square. I mean, since I'm expressing everything in terms of centimeter, I need not to worry. So if you compute this, you will get the answer as 6.25 ohms, right? So your R is 6.25 ohms. Fine. Okay. So now what about the component 2? For component 2, you can write that it is a capacitor, right? It is a capacitor and with capacitance falling is equal to square root of Q ND epsilon whole divided by 2. Yeah, your 5BI plus VA, right? And just a second. For component 2, the description was this, right? For second component, we have been given that it is a tiny bar of semiconductor made of same material and doping concentration as of the first component. So it is N-type and has a donor concentration of 10 to the power 15. Now, with this semiconductor, we established two contacts on the opposite ends. Fine. On one end, we have a silver, and on the other hand, we have a gold. Right. Upon looking up a lab handbook, the student gives us the following data: that the work function of gold is 5 electron volts, work function of silver is 4.7 electron volts, work function of semiconductor is 4.8 electron volt, relative permittivity of semiconductor, right? That is your 10 times permittivity of free space. Fine. So EC minus EF at the bulk of the semiconductor, that is 0.2 electron volt. Permittivity of the free space is given, and we have been given that the square root of 72 is equal to 8.5. So let's see what we can do. Firstly, let me make a, I guess, band diagram. So this is the corresponding band diagram. This is your EVAC. This is your Fermi level, right? Constant throughout. And yeah, this is EVAC. This is EC, right? And this is your interface. Okay, this is your EC minus EF bulk, right? And this is your EC. This is your EV, right? This is your EVAC. This is your, yes, Caius can also be drawn, right? Let's draw Caius as well. This is your Caius. This is your This is what? This is your, I'll write this as BI, right? And work function phi s, that is also given. Let me use this one for that. Phi s is this. Yeah, remaining is done. This is your EF, right? And this was your EF on the metal side. Okay, so now, I mean, we can calculate this by BI from the band diagram, right? As follows. Let me write. Uh, we can calculate this IBI from the band diagram, right? So this is phi BI, and that phi BI is equal to phi B minus EC minus EF bulk, right? Your chi-s, right? Your chi-s is equal to your phi m minus phi b. That is your phi s minus EC minus EF bulk. Okay, someone is saying that in earlier problem, I had taken a different region for QB. In which problem can you just, at least write the problem number perhaps? Do you mean this one? Second. Okay, this one. So what did you write? Next one. Okay. So this one, right? Question 3. Okay, fine. Question 3. What did you take for this? In fact, I guess if I correctly remember, you QB. Why would you compute QB for it? Okay, I guess probably you mean phi B, right? Phi B. IPS if you mean phi B. Okay, you got it. So is this clear? How we came to the 0.8 volt? In fact, probably you were the one who said, right? We'll take the difference and compute it as 0.8 volt. So that's why I thought you understood this. Is it clear? Fine. Thank you. So now for this one, right? Our chi-s is equal to phi m minus phi b, right? So which is equal to our phi m minus phi b. What is phi m minus phi b? Right? This is your phi m. This is your phi m. What is your phi b? This. So what is phi m minus phi b? Phi m minus phi b would be in fact this chi-s, right? Electron affinity, right? This distance minus this minus this, which is equal to this, which is nothing but chi-s. Now what is chi-s, right? This electron affinity can be written as, mm, you can write this as this part is equal to, okay, wait, how should I? Okay, this chi-s is same here as well, right? This is chi-s. And what is that equal to? That chi-s would be equal to our phi-s. See, what I mean is this would be same here as well, right? So I can write this as chi-s. In fact, I should write q psi-s, right? Otherwise, this is q throughout, okay? Please don't get confused. This is q phi b, everything has q multiplied. Okay, please don't get confused. So what is now this part in terms of this and this? Does anyone have mic? I mean, it would be really helpful if anyone among you can unmute and just tell me, because otherwise writing in the chat is tedious, right? Okay, just write yes if what I will say makes sense. Okay, so I'm saying this q psi-s, I mean, sorry, q chi-s would be this whole minus this part. Does this make sense? I'm saying this q chi-s would be equal to q phi s minus EC minus CF bulk. Yes, okay, so this does make sense, right? So as I said, this phi m minus phi b is chi-s, which is nothing but q phi s minus CC bulk. That's why I wrote phi m minus phi bulk as this, right? This makes sense. So now I'll plug in the values. If you'll plug in the values, you'll have following. This would be 4.8 minus 0.2. How is this 0.2? EC minus CF. You can use that formula, right? This EC minus EF, express this in terms of, I mean, the given quantities, right? You know, what is this? I mean, donor doping, right? It is N type, so it has been doped with donor dopants. Okay, so since you know the concentration of donor dopants, which is 10 to the power 15 in this case, so you will be having an idea of where this Fermi level lies, right, with respect to EC. So once you know that, you can easily compute this EC minus EF bulk. So it turns out that EC minus CF is 0.2. I'll leave that as an exercise for you all. Okay. Please make sure you do this in between calculation, what I just mentioned. So it's 4.8 minus 0.2, which is nothing but 4.6 electron volt. Is this clear? Please respond so that, uh, I mean, I'll get to know that you are following. Okay, fine. I'll continue. So now we know chi-s, right? Uh, remember see, what is the objective? The objective is to calculate this, I mean, this particular quantity, right? So I'll write now the following. What is your phi b, the barrier height? Can I write that as I'm sorry, phi m minus phi s, right? Pretty straightforward. We already did that in the previous question, right? This phi b is nothing but phi m minus chi s. So this is equal to 0.4 electron volt. Right now, if you plug this in equation 1, right? If you plug this phi b in 1, right? If you do this, you'll get following. We'll have this phi bi, that is equal to 0.4 minus 0.2, right? 0.4 minus 0.2, which is nothing but 0.2. 2 electron volts, isn't it? So I can write that SPI would be 0.2 electron volt. Fine. What else now? Now we'll put this into the capacitance equation, right? Into this equation. See, I needed this one. I know this, right? What is VA? Do we have info about VA? We have, right? It's 0.8. What about this 5BI now? This is 0.2, right? If you put these values into this equation, let me mark this first, right? Let this be equation A, right? So our A becomes what does A become? A becomes following, right? A becomes A, sorry, your C is equal to square root of, now I'll be putting in the values, right? So this is 1.6 into 10 to the power minus 19. What else? I'll have this 10 to the power 15, right? Corresponding to this ND. What about this epsilon s? This would be relative permittivity, right? Just tally with the question, right? It turns out relative permittivity is equal to 10 times, and the free space permittivity, that is 9 into 10 to the power minus 14. It's given in the question. Okay, let me just show you. Look at this one. This is permittivity of free space. This is the relative permittivity of the semiconductor. So that is what I did here, nothing else. And this is whole divided by 2 times 0.2 plus 0.8. Fine. And C would be equal to, it would be root of 72 times 10 to the power minus 9. And it's given that in the question that we can take this under root of the 72 as 8.5. I'll do that, right? I'll write that this is equal to 8.5. Let me say this is nanofarads, right? So we are done with C as well. Now, what are we interested in? We are interested in computing the time constant, right? We need to compute the time constant of the parallel combination of component 1 and component 2. What is component 1? Component 1 is resistor. What is component 2? That is a capacitor. When you put them in parallel, what is time constant equal to? If R is the resistance of the resistor and C is the capacitance of the capacitor, what is the time constant equal to of a parallel combination of a resistor and a capacitor? Can you just type it in the chat? Simple, right? What is tau equal to for this RC parallel combination? Please write an expression of tau in terms of R and C for this parallel combination of component 1 and component 2, which is nothing but a resistor and a capacitor in parallel. Anyone? No one? Okay. Will this be tau equal to RC? At least write yes, if it makes sense. Would tau be equal to R into C? You must have seen this, right? When capacitor and a resistor are put in parallel, the time constant is equal to RC. If not, just revise it again. Okay. This is something that is trivial and you are expected to know. So I'll just directly write now. Fine. Time constant of parallel combination, that is equal to RC, which is nothing but what is our R? 6.24 multiplied by, and our capacitor, that is 8.5 under 10 to the power minus 9. Right. Which is 53.125 nanoseconds. Okay. That is this time constant tau. So I'll write this is tau is 53.125 nanoseconds. Done. Yeah, I hope this is clear. Let me move on to the next one, right? So the second question of this comprehensive question, which we just went through, there is second part to it. Now it's saying that, say I replace now the gold contact by the silver contact and leave the other silver contact intact. And then I excite the parallel combination of component 1 and component 2 by a small signal voltage source A sine of omega t plus 10. As you can see, the phase of the input signal is 10 degrees. So the question is, what is the phase of the output signal that is measured across the parallel combination of a resistor and a capacitor? I mean, it might sound complex, but this is pretty simple. See what this question is saying. See, after we replace the metal in the contact will no more be a Schottky, right? It's now an ohmic contact, right? I'll write it is no more a Schottky contact. It is an ohmic contact, right? And yeah, it is an ohmic contact. The behavior is now similar to that of a resistor, right? So we won't have capacitive action anymore. It will just be merely a resistor. So I'll write that as well. Why? Because this contact is ohmic now. So I'll write the behavior is now similar to that of resistor and no more like a capacitor. Okay. So what would be the circuit for, the effective circuit for the phase would be following, right? Let me write that. The effective circuit for phase would be following, right? You'll have this. This is your A sine of omega t plus 10, which is nothing but an input. This is your R1. This is your R2, right? This is this, and this is this. Nothing but output, right? This is your output, and yeah, we are interested in the phase of the output, right? From the basics of, the electrical, from the basics of how the electric component behaves, है ना? That is nearly a resistor, right? We know that the phase won't be affected at all, right? See, R1 and R2, the parallel combination would still be some resistance, right? And unless it were a capacitor or an inductor, the phase would not get affected, right? So the phase of the input and output are same, right? I hope the reason is justified. The phase of the phase of input and output are the same, right? So therefore your phase of output signal would be same as the phase of the input signal, and that would be your this 10 degrees, right? Makes sense, right? Why will this be unchanged? Because it turns out that this component 2, which earlier was a capacitor, now this contact, since this contact is an ohmic one, this would be a resistor. So a parallel combination would again be some resistor, right? So it would be some equivalent resistance. And we know that resistor cannot change or affect phase. So that's why our phase is unchanged, which is same as input, that is 10 degrees. Now we come to the last question, right? Question number 6. Which of the following statements is or are true with regards to the formation of the ideal metal semiconductor junctions using a metal with a work function phi m and a semiconductor with phi s? Okay, so this in fact is pretty straightforward, and uh, I expect that you all should be knowing this, right? Because this was recently taught by professor. So if the metal, uh, I mean, if you have a p-type semiconductor and a metal semiconductor junction with that p-type semiconductor, and if phi m is less than phi s, it is Schottky, right? So this one is correct. Similarly, if phi m is greater than phi s, it is ohmic, right? A metal n-type semiconductor junction with phi m greater than phi s is ohmic. No, this is incorrect. This would be a Schottky one. And a metal n-type semiconductor junction is, I mean, is it Schottky when phi m is less than phi s? No, it would be Schottky when phi m is greater than phi s, right? So these two are interchanged, right? So that's why this is wrong, this is wrong. So first two options are correct. Sir, can you please tell in band diagram how we should calculate the depletion region and the electric field when the junction is reverse biased. How we should calculate? Do one thing, just drop me an email. Since this is, I mean, deviating from a topic, I'll address this. Or we can do one thing. Uh, in the next live session, what I'll do is uh, join 20 minutes early. I'll explain this part. Fine. But do mail me this query. Fine. I'll address it there. Any other question that you all have with regards to, I mean, the questions that we taught today? If there are no more questions, we can wind this session here. We are done, right? There are no more questions left. In the previous week 4 live session, I had given you one problem that was left as an assignment for you all. Was anyone able to do it? Did anyone try it out first? Yes, no, any answer? Remember, I had left this as a homework, right? Although in fact, this was actually, uh, wait, was this problem in your current assignment? Why did I leave this as a homework? I guess this was in your current set of assignment, right? Your week 4 assignment must be having this problem. Yeah, that's why I left it as a homework. So did anyone try it out? I mean, or in other words, I should say, is the deadline over for this? Okay, the deadline is over. So I'll assume you were able to solve it since nobody raised a query regarding this homework. So I'll assume that you all were able to do it. Fine. So since we are done with week 5, let's call it a day. Fine. Thank you. Thank you for joining. Have a good day. Bye. Thank you.